How you guys doing today? Did you guys have a good long weekend?
It was lovely.
I know, it was nice to sleep in, right? All right, while we're waiting for others to arrive, let's just talk about what's coming up in the next week or so. We've got some things coming down the pipeline here. So let's see, today is this week. Right, today we've got chapter 4.5 and tomorrow we have chapter 4.6. They're gonna be stuff that we're going to cover on these chapters that we're going to have to come back to these chapters after we do chapter 5, which is totally fine. Anyway, so my question for you is about, again, sorry, we've got homework. When's the homework due? So chapter 4.5 right now is set up to be due tomorrow. 4.6 is set up to be due next week, but I wanted to ask you, do you want the homework to be due, both of them due next Thursday, next or this Thursday? You guys can vote on it. Why don't you write it like maybe in the chat or something? You can do it if you want. You can write it privately to me if you want to write something you think might be unpopular, or you can write it to publicly next week. And we're going to go by pure majority rule here. Next Thursday. Okay, it looks like I'm seeing a lot of next Thursday stuff. Okay, so I'm going to check. This one's already set up for next Thursday, but I'll change 4.5 to be next Thursday as well. All right, also, let's talk about a quiz. Yes or no? I can probably already tell what the answer is going to be, but let's talk about quiz tomorrow. And I guess the quiz tomorrow would probably be on maybe chapter 4.4, maybe 4.5. But let's vote. You guys want to do a quiz tomorrow? Okay, it looks like majority rule next week. We're getting, oh, sorry, no, I'm circling there. Okay, sorry, almost voted yes. Okay, quiz tomorrow, no. So homework will be due next Thursday. We're not going to have a quiz tomorrow. So you kind of have the week off a little bit in terms of things that are for things that are doing. Sorry, I'm reading stuff in the chat. Let's see, and then so 4.1, yeah, you know, so 4.4 is still due tomorrow. That's right. So chapter 4.4 is due tomorrow. Sorry, my pen keeps sticking. Sorry, due tomorrow. So 4.4, you're right, is still due tomorrow. So think about that. If you guys want to ask questions on that, we'll see if we have time at the end of class, although I ran out of time on my 9 o'clock class. So you guys can come to office hours if you want to ask about 4.4, but that's still due tomorrow, okay? But these 4.5, 4.6 all changed to be due till next week. No quiz tomorrow. Okay, now let's talk about next week. Okay, we can see it on our syllabus. So we only have homework 4.5 for next week. Oops, sorry, everybody's writing too much. It's going to, okay. Yeah, so let's see. Yeah, so the quizzes are worth different number of points, depend on how many chapters they cover. That's true. I tend to be 10 points each for each question. So like last week's quiz, I only made worth 20 points because I know that was going to be really hard. So I didn't want that necessarily to impact you pretty hard if that was going to be hard for you. So yeah, so our first midterm. So this is next week. So our midterm. Next Thursday, so a week from tomorrow, next Thursday is our midterm number 1. And that's going to cover everything up to and including chapter 5.1, okay? Because next week we're going to cover chapter 5.1 on Monday. And then we're going to do review on Wednesday. And then Thursday, we're going to have our exam. The next chapter also going to be a part of it. Let's see. So next Thursday we have the quiz and the midterm. No quiz next week. The next week is just the midterm. So what's going to happen next Thursday is we have our midterm, right? And then we probably will not have class on Thursday. Okay. Usually when I have a midterm, I don't have class because I open up the midterm right when the class starts. So if it's convenient for you to take the exam during the class period, you can absolutely take the exam during the class period. Okay. I'll open it up. So basically for us, our midterm is going to start at 1:35 p.m. Eastern Standard Time. It's like there's going to be a window of availability, right? 1:35 p.m. Eastern Standard Time on Thursday. And it's going to go until 1:35 Eastern Standard Time on Friday. This is the availability window for the exam. Okay, but what happens though is that unlike our quizzes, this is going to be a timed exam. Okay, and so we'll have 65 minutes plus 15 minutes for tech. So that means that, like for downloading, like printing, you don't have to print if you want to, downloading, taking a picture, uploading. Okay, so you'll have basically 80 minutes to do the exam, including download and upload and taking pictures and whatever, but it's timed. So you only get one shot. Okay, so that when you open up the exam, the timer starts ticking. And if for some reason you get, you stop, right? And you stop doing things or you submit it or whatever, you can't go back in. Okay, so make sure that you upload everything, all your answers within that 80-minute time period. Okay, if you have DRC accommodations, time accommodations, please email me offline so that we can make arrangements for you for handling that. Okay, but everybody else, once you guys start the timer, then you have to finish it within that time. What is the syllabus for the midterm? I think you mean the topics we're going to cover. So we're going to cover everything up to and including chapter 5.1. So we do 4.5, 4.6 today and tomorrow. 5.1 we do on Monday. Wednesday we do a review, and then on Thursday we have our exam. Okay. If you guys take a look at our Canvas page for next week, oops, sorry, our Canvas page for next week. This looks a little blurry. Hang on. Our Canvas page for next week. I have old exams. Okay, old exams on our Canvas page. I think there may be like 4 old exams on there, so you guys should be able to take a look. I think I've got solutions up for those too. So over the weekend, right, you'll want to take a look at your homeworks. You want to get all those things submitted. I think like Wednesday, I will submit, I'll make a modules page at the very beginning of I'll make a module at the beginning of our modules page for like homework solutions. So I'll give you guys solutions to a bunch of the homework problems. So you can then check your answers, because I've only been checking your homeworks for completion, not for correctness. Okay, so you'll want to be able to check those, but I'll post those solutions, post those solutions for that. So anyway, yeah, will the homework 5.1 also be due on Thursday? You know, since it's going to be on the exam, yeah, it'll be due on Thursday. You definitely want that. So then the homework 5.1, that'll be due at midnight, like all of our homeworks. Okay, so then let's see what else. I think that's about it. So 4.5, 4.6, and 5.1 I'll do next week. 4.4 is going to be due tomorrow. Okay, no quiz tomorrow. Next Thursday is our midterm exam covering everything up into and including 5.1, okay, which we're going to start on Monday. Next Wednesday is a review where you guys are free to ask me any question, like on the old exams. You can ask me questions from like homework problems, from the quizzes, from whatever. Okay, you guys can do stuff like that. If we move 4. Wouldn't that mean we would have 4.5, 4.6, and 5.1? What do you mean? Yeah, so those all would be due on Thursday, right? So these are due next Thursday. That'll be due next Thursday, and they're also going to be on the exam. Okay. All right. It's a lot of stuff, but it's, I think, you know, workable. Anyway, let's see. I think that's about it. So I'll go change those homework things after class. Okay, and then I'll post our videos. I'll post our video after class as well. Also, if you guys want, on my YouTube page, I posted a copy of our video from last week, which was basically how do we decide how do we calculate that max f of n plus 1 of z? How do we calculate the z? How do we calculate that max value? All those things are posted up on my YouTube page as well. I think it's lecture 11 on my Calc 2 lectures. So take a look at that if you want to get an idea for those things. All right, so that's administrative stuff. Oops, sorry, and then there's somebody there. So now, I want to be able to, sorry, for those of you just coming in, just a quick summary, 4, 5, 4, 6 are due next Thursday. Okay, chapter 5.1, which I'm going to assign on Monday, that'll be due next Thursday as well. Next Thursday is a midterm exam covering everything up to and including 5.1, and we don't have a quiz tomorrow, but homework for chapter 4.4 is due tomorrow, so keep that in mind. Okay, so I want to talk really briefly about the quiz that you guys just took. 4.2 and 4.3, I want to go over it because I want to make sure that we really have this idea down pat about how do we calculate the error and how do we calculate the, how do we make a, I guess in this case, this is a Maclaurin polynomial, okay? So let's go through, this is the quiz I posted solutions for, but I want to be able to talk it through because I think that'll help. So this question was really just one question. So we have f of x equals the natural log of 2x plus 1. And this says x has to be greater than minus 1/2. And that's right, that comes from our function itself because our natural log is not defined for values, right? Less than minus 1/2. Okay, we're heading into an undefined territory. So we just specify our domain here that applies to this point. Okay, so part A says we want to find the third order Maclaurin. So we're looking at, I'll write 0. Okay, because this is our third order. I didn't have to write the 0, but I'm writing it out. So third order Maclaurin, let's write this out. So this means I'm going to go f of 0 at 0, f1 at 0, x to the 1 plus f second derivative at 0 all over 2 factorial x squared plus third derivative at 0, 3 factorial x cubed. Okay, so we have to come up with these coefficients here, and that'll give us our Maclaurin polynomial for it. So let's set up our table. So our derivatives. Okay, and then, excuse me, this is going to be x equals a equals 0. Our 0th derivative is just our function, natural log of 2 times, oops, sorry, x plus 1. Evaluate at 0, natural log of 2 times 0 plus 1. Natural log of 1 is just equal to 0. So this term is going to be 0. Our first derivative, when I take this first derivative, this is going to be 1 over 2x plus 1. My chain rule, right, times 2, which I'm going to write out like this. 2x plus 1 to the minus 1. Okay, because I know I'm going to be needing to do a bunch of derivatives. Okay, so now I'm going to evaluate that at 0. So 2 times 2 times 0 plus 1. So that's just equal to 2. My second derivative. Okay, so I've got the 2 from before. I've got the I have a minus 1 from my exponent. I have a 2 from before. I have a 2 from my chain rule. And I have a minus 2. So my second derivative evaluated at 0 is going to be minus 4. Minus my third derivative. Right, let's write what we have. So I've got a minus 1, I've got a 2, and I've got a 2. These are all things I had before. And now I have the minus 2 from my exponent. I have the 2 from my chain rule. I have 2x plus 1 to the minus 3. Okay, third derivative at 0. Minus minus is positive, 1, 2, 3, 4. So this is 2 to the 4th, which is 16. Okay, now I'm done for figuring out my coefficients from my Maclaurin polynomial, but I know part B says come up with a third order error for this, which means I need to come up with my fourth derivative. So I'm just going to calculate my fourth derivative while I'm here, but I won't plug in x equals 0 because I don't need it for that. So my fourth derivative, so I've got 2, 2, 2, 2. So I did minus times minus. Now I have a minus 3. I have 2 from the chain rule, 2x plus 1 to the minus 4. So this is 1, 2, 3, 4, 5. So this is a minus 3 times 2 to the 5th all over 2x plus 1. Sorry, you can't see that. 2x plus 1 to the 4th, which is equal to minus 96 times 2x plus 1 to the 4th. Okay, so this is my fourth derivative at x. Okay, this is for part B. I'm not going to worry about it right now. These things I need to come up with my coefficients. I need these things. So let's go ahead and put that into our third order Maclaurin because then we have to answer stuff for part A. Okay, so my third order Maclaurin. So f of 0 is 0. F prime at 0 is 2x. F double prime at 0 is minus 4. x squared all over 2 factorial plus f triple prime 16 all over 3 factorial x cubed. So now I'm going to clean this up. I'll multiply through my third order. I don't need the 0 anymore. So 2x, this is minus 4 divided by 2, so minus 2x squared. This is 16 divided by 6. So 16 over 6 is 8 over 3x to the cube. And that answers part A, my third order Maclaurin. Okay. Okay, so let's go ahead and give you guys a minute to finish writing that. And then we'll talk about part B, which is the error. Okay, so let me just write that down again. So f to the 4th of x is equal to minus 96 all over 2x plus 1 to the 4th. Okay, so now I just want to rewrite that from before so I can remember it. Okay, so now we're told absolute value of x is less than or equal to 0.1. We're going to need that to figure out some stuff, right? And then we want to come up with a third order error for our Maclaurin. Now remember, our third order error is x to the n plus 1 factorial, right? And this is max absolute value f n plus 1 of z. Okay, so n is equal to 3. Absolute value of x less than or equal to 0.1. So I'm going to plug in 0.1 here. So this is going to look like 0.1 to the 4 all over 4 factorial max f to the 4 of z. Okay, so we're starting on that path. So let's talk about how I calculate max f to the 4 of z. Okay, absolute value. All right, so first let's talk our f to the 4 of z, absolute value. I'm going up to here and I'm going to replace x with z minus 96 to z plus 1 to the 4. Okay, which means I'm dealing with 96 to z plus 1 to the 4. Okay, now I have to figure out what to do for z. So let's do this here. Absolute value of x less than or equal to 0.1. So I'm going to rewrite this to be minus 0.1 to positive 0.1, right? Because that's what this means. All we did was just rewrite it. Okay, I'm going to substitute in z for my x. Okay, now remember, what does this mean? This means, right, here's my coordinate grid. This is my x and y axis. Our a is equal to 0. So we're focused at a equals 0. And this says we're going to look at values of our function between minus 0.1 and positive 0.1. So we're looking at this narrow range of values. I didn't draw that very well. Narrow range of values, really close to 0. Okay, and we want to be able to look to see how well our polynomial converges to our function. How well does it sit on it? What's the error in that approximation within this range of values here? Okay, so my z value is going to be between here. Now what I want to do is I want to find a value that's going to maximize my function. So I need to look at my derivative, right? My derivative is in the form of 1 over z. So I need to rewrite this as 1 over z. Okay, and I have to take the reciprocal of everything. I can't just make this 1 over z and leave these the same. So this is all 1 over z. So now I need to decide which one of these, this one or this one, which one of these values is going to maximize my, my function. So I'm just going to check. Remember, this is a natural log function, right? So I can actually plug in one of my extreme values on my boundary here. It's not like my e to the x where I have to find a value that's just outside of it, or trig function where I'm looking at the amplitude. So I'm going to check. So I'm going to do, if I do a z equals minus 0.1, that's going to give me, right, I'm going to go 96 all over 2 times minus 0.1 plus 1 raised to the 4th power. And let's see, what do I get? I got 234.24. Okay, that's with the negative 0.1. And now let's do z equals positive 0.1. That's this one. So it's going to be 96 all over 2 times positive plus 1 to the 4th. Don't always assume that just because this is positive, it's going to maximize it. We have to check. We have to check to make sure to see. When I do it, I get 46.29. So this one here is bigger, which means z of minus 0.1 is the one that I want to use. So I'm going to choose this right here for my z. Okay. Whew. All right. So now what that means is my max absolute value of f to the 4 of z is going to equal to positive 96 all over 2 times minus, sorry, there's a minus in there, plus 1 to the 4th, which comes out to look like 96 all over. When I multiply 2 times minus 0.1, I add 1, 0.8 to the 4. That's just this portion. So now I'm going to take that and I'm going to plug that into here. Right, so this is what I had for my third order. Let's write that all down again. All right. Okay, so my third order error for my Maclaurin is going to, we want that to be less than or equal to, we said 0.1 to the 4 all over 4 factorial times 96, 0.8 to the 4th. That's a 6. And I'm just going to plug that into my calculator, and I got 9.7656 times 10 to the minus 4, which is 0.1239766. Either one of these is fine. All right, so it's the quiz. I wanted to go over it. I know I posted the solutions for it and I'm still grading it, but I wanted to go over it and talk about it so that we can be on the same page, and so you guys can hear the solution as we work it through. Because this stuff is always confusing to think about, and it takes a bit to get our mind to work through. Okay. Whew. Okay, guys. So you can take a look at the notes that I posted online for that too. All right. So with that said, let's go ahead and get started on chapter 4.5. Let's see there. Okay, so chapter 4.5 is called Power Series as Functions. Part 1. Part 2 is chapter 4.6. We'll do that tomorrow. So we're going to cover something called the ratio test today. And then this is also going to come up in chapter 5. I think it's 5.4. I can't remember. What's going to happen in this chapter 4.5 is we're going to talk about the ratio test, what it means, why we're doing it, and then we're going to use it. But there are parts of chapter 4.5 and 4.6 that require knowledge that we're going to get in chapter 5. Okay, so what we're going to do is this. I'm going to cover everything in 4.5 and then tomorrow in 4.6 from what we can do based on what we're learning so far. I'm going to tell you where we're going to skip, and then we're going to come back to that skip stuff after we do chapter 5. Okay, so obviously I won't test you on those things that we haven't learned yet. Okay, but keep in mind that we're going to come back to these 2 chapter sections after we do chapter 5. Okay, so remember our power series. Remember, our power series is an infinite polynomial. It's like x raised to a power, right? This is our x to the n, say for example, okay? So our power series, we say it's going to be equal to our function, or it's going to converge to some function, n equals 0 to infinity. I've got my coefficients, x minus a to the n, okay? Where, right, a is where we're centering it, c sub n is our coefficient. Our Taylor and Maclaurin, our coefficients come from the function itself, that's derivatives evaluated at a. So this is c sub 0, x minus a, c sub 2, x minus a squared, plus so on and so forth. Okay, all the way up to infinity, right? All right, so what are we trying to do? What are our goals? So our goals here are, the first one is that we want to treat a power series as its function. right? We're using our polynomial to estimate some function itself, right? And why do we do that? We do that because polynomials are really easy to work with, right? They're nice to work with because I can, you know, take derivatives, I can integrate, I can do all sorts of stuff with a polynomial very simply that to do it on a complex function is much harder. But I want to be able to treat this polynomial, infinite polynomial, as its function equivalent. I want to just work with this polynomial. So now, in order to do that, I have to look at where does this polynomial converge? And when we say converge, we're saying what range of x values is this power series equal to its function, right? Because maybe it's like the Maclaurin for sine or cosine or all those other functions, it's equal to it for all x values. Maybe it only works for some small range, or maybe it doesn't work at all. So we need to be able to figure that out. So let's write down. So we've got our power series, our polynomial. Power series defines a function where they converge, where the power series and the functions converge. Basically, you think of that as like where the power series converges to our function. Okay. So why else do we want to do this? Because we want to be able to do function operations on the power series. Like we want to be able to take the derivative. We want to be able to integrate. We want to be able to add, subtract. We want to be able to multiply or divide. Okay, it's really easy to add, subtract polynomials, add or subtract, multiply or divide polynomials, certainly integrate and take the derivative of polynomials, right? So that's what we want to do. And what we're going to do after chapter 5 is we need to be able to check how these operations change the range of convergence, which we call actually the technical term for it is our interval of convergence. This is later after chapter 5. We're going to come back to this part. So we're going to learn how we can figure out what's this interval of convergence today, right? But how we check it after we do stuff, right? How we get more detailed information about the interval of convergence, we're going to come back to after chapter 5. We need the skills from chapter 5 to teach us how to do this part here, okay? So those are our goals. Let's talk about our domain. So our domain of our power series, really the important part is what are our x values, right? All of our x values over which our power series will converge, right? I want to know what are the range of x values over which this polynomial is equal to its function, right? That's the most important part. I'm going to use that to define my domain. My range of possible values, all real numbers, okay. So let's start talking about how we can tell where things are going to converge, right? And then how we calculate that. We're going to learn, start learning about the ratio test and all that. You guys have this? Okay. All right, so let's start talking about what we call the radius of convergence and the interval of convergence. So the radius and the interval of convergence, okay? All of these things we're gonna need to know. I'm gonna talk about sort of conceptually what they mean, and then we're gonna talk about how we calculate them. Okay, so there are 3 different ways that we can think about our radius of convergence. I can think about my power series converging onto my function at a single point. We're guaranteed a single point convergence. This is our single point, this is A. Where we center this. So where we center our polynomial, we are guaranteed it. And why is that? It's because we create our power series with A in mind. We say that the function and the power series sit on top of each other at A, their derivatives, all their derivatives sit on top of each other at A. So let's just write that down in math. So we'll say every power series centered at A converges at x equals A. It says our single point convergence. Since all other terms are 0, except the first, that would be our c sub 0 term. Okay, so it looks like this. Remember our polynomial, c sub 0, c sub 1, x minus a, plus c sub 2, x minus a squared, plus so on and so forth. If I plug in x equals a, I'm going to get 0 here. 0, 0, 0, 0, all the way down. And all I'm left with is our function evaluated at a. Okay. So what this looks like in terms of our number line, these are all possible x values. We're centering at a, and we're basically just converging right here. Okay. So our function does something, our polynomial does something, we're guaranteed a point convergence at A. It's pretty narrow, it's not very interesting, but it's, you know, it's our minimum. Okay, single point. The next level up is we can get an interval of values over which our function, our power series will converge onto our function, right? So this is an interval of values of x over which our power series converges to our function, which means I can treat my power series and my function as equivalents, right? And what this looks like is this, right? So here's my possible x values. Here's where I've centered it. Here's my radius. So I'm going to go a plus my radius. Here's my radius. This is a minus my radius. So my interval of values becomes from a minus r to a plus r. Okay, this is my interval of values over which my power series and my function are going to sit right on top of each other. Okay, so where it'll converge. And this is where we talk about boundary conditions that we need chapter 5 to help us with. I have 4 possibilities. I've got a minus r, a plus r. The square brackets means both are included. Oops, I'm not leaving myself a lot of room here. So both endpoints included, okay? Or I could do a minus r, a plus r, only the right-hand side is included. A minus r, a plus r, only the left-hand side is included. Or neither, it's an open interval. Okay, for what we're trying to do in this chapter, because we don't have the chapter 5 materials to tell us, am I including it or not? We're just going to write it like this. Whatever the numbers are, 2, 4, a minus r, a plus r, okay? And then when we come back after chapter 5, we're going to figure out how to put our brackets, open or closed intervals, okay? So that's what that looks like. So we have a point convergence, we have an interval of values. Now our third and last possibilities are all values, our full number line. What that looks like is x is centered at A, but all possible values are okay. Of x, which means that our radius, this is our radius, right, that's our radius. Our radius is infinite. Okay, which means all possible x values. We see this with Maclaurin for sine of x, cosine of x, e to the x. Some of these functions are actually equal. The Maclaurin is actually equal to their function, okay? Okay, so 3 possibilities. We're going to write up what this looks like. We're going to write it a little bit more formally in terms of convergence. You guys all have this okay? Okay, so let's write this up in terms of our convergence. And we'll do this, I'll write this formally. Okay, so what this means is our power series converges at A. This is our radius equals 0. This is like what we just wrote, okay, but I'm gonna write it a little bit more formally. Our power series converges at A. This is like x equals A. Radius is equal to 0. Our radius, our r, is some positive value. It's gonna be, you know, some positive value. And what we're gonna say is that the series, our power series, converges absolutely if we're going to say x minus a is less than r, right? So this is where we're centered. This is our power series. So if a is equal to 0, if a is equal to 3 or pi over 2 or whatever, right? So wherever we're centered it, okay, is less than our radius. We're going to say that our power series is going to converge absolutely. Absolutely just means we're using absolute values. So it's going to converge when this is less than r. And we're going to say the series diverges. We don't say diverges absolutely, it doesn't matter, when x minus a is greater than r. Okay, so outside of, we've seen this before when we graphed this stuff, right? So within some range of values, we have our function, we have our power series. It sits right on top of it. They're equivalent within this radius, within this interval of conversions. Outside of that, our function and our power series pull apart. So the error of approximation gets bigger and bigger. Okay, so that's why I'm looking for what's that interval of convergence, because I want to know under what values of x can I use this power series and my function interchangeably. Okay, because outside of this, the error gets so big, it's not worth it. Okay, so this is what we're talking about here. Within our radius, it converges. We can use it as a function. Outside of that, it diverges. We should maybe, you know, rederive our power series. Okay, or our third possibility for the number line is that our series converges for all x values, which means our radius is infinite. Okay, this is just like what we just wrote up, but I'm kind of writing it in words. Okay, so we say r is our radius of convergence. Okay, and it's going to define our interval. Interval of convergence. So how do I figure out what the radius is, right? So we're going to use what's called the ratio test to determine our radius. Okay, ratio tests we're also going to cover in chapter 5. Okay, so when we get to chapter 5, we'll be completely confident and understand what to do with the ratio test, and then we're gonna talk about it. So right now, what I'm gonna do is I'm gonna go through, give you out the theorem for the ratio test, and then we're gonna work on, I'll show you examples using the ratio test using just basic series. Then we're gonna apply it to our power series, and we'll be able to see what it looks like. Okay, so this is actually a theorem ratio test, okay? So let's say A sub n is some series, okay? And the series has non-zero terms, okay? I mean, I have a series with 0 terms, but it isn't as interesting. So I want this to be non-zero terms. Also because we're gonna put this in our denominator, so I don't want that to be 0. Okay, so my ratio test for the conditions for convergence and divergence, it goes like this. I take the limit as n goes to infinity of the absolute value, a n plus 1 all over a n. This is my current term, a sub n. Where am I at right now? This is my next subsequent term. So this is a sub 2, a sub 3, for example. So what I'm doing is I'm comparing my next term with my current term. And I want to see if the ratio of these terms is less than 1. That means each subsequent term is decreasing. Okay, so it's starting to decrease. It's starting to converge to some value. Okay, so then therefore we can say, then series converges. Okay, less than 1, series is going to converge because this is absolute value, less than 1. So it's getting smaller and smaller. Limit as n goes to infinity. Next term up from current term. If it's greater than 1, right, that means the terms are getting bigger as I go. Then series diverges. Okay, which means I can't use this series to approximate a function within that range. Okay, or it's only valid at my x equals a. Next term up to current term, there's no change, right? Whoops, I get the same ratio. Each subsequent term is the same ratio. The ratio test is actually inconclusive. You have to use another test. This is chapter 5. Okay, so we're going to learn in chapter 5 a whole slew of tests that we can use to check to see if series are going to converge or diverge. We haven't learned that yet. We're just learning the ratio test right now. Okay, so so I've got my lecture examples for chapter 4.5. And what I'm going to do is all of these lecture examples, right? These are not power series. They don't have an X component in them. They're just generic series, okay? So we're going to go through and we're going to talk about how we actually use the ratio test on generic series. And then we're going to apply it to a power series, okay? All right, so example 1A. Okay, so my ratio test says, I always want to know, is it going to converge, diverge, or is it inconclusive? Okay, so I have to convert this. This is a limit process. Now we're using K here, K to infinity, absolute value. So everywhere I see a K, I change it to a K plus 1 all over my current term. So 1 over 3 to the K plus 1 all over 1 over 3 to the K. This is a sub n plus 1 all over a sub n, okay? So what this means is, right, I have a fraction divided by a fraction, so I'm going to multiply by its reciprocal, okay? So this is the limit as k goes to infinity. So this is going to be 3 to the k all over 3 to the k plus 1, absolute value. So 3 to the k, I'm going to break this up. This is 3 to the k times 3 to the 1, right? I can do that. This is their equivalent, which means these are going to cancel each other out. So this is equal to the limit as k goes to infinity of 1 over 3. Okay, which my k is canceled out. So I'm basically dealing with this thing is equal to 1 over 3. Okay, 1 over 3 is less than 1. Therefore, this series converges. Okay, you have to write this. You have to write this. Right? You have to write that your limit, what your limit's equal to, how that fits in with our criteria, and what's your conclusion. And then you have to obviously show your work on how you got there. Okay, we're just gonna go through 1, 2, 3, 4 problems here. All right, so this next one, 3 to the k. So it's different. That was 1 over 3 to the k. This is just 3 to the k. So I convert this to a limit. K goes to infinity, so this becomes 3 to the k plus 1. All over 3 to the k, all right? So like before, k goes to infinity, 3 to the k times 3 to the 1 all over 3 to the k. These cancel. I get that's 3 to the 1, or 3, right? Which is greater than 1, and this diverges. Okay. Chapter 5, we're going to be learning all about what types of series these are. Okay. So let's talk about this one's got a factorial in it. That's good. Anytime you see a factorial, ratio test works really well for processing it. So the limit as k goes to infinity. remember, my first batch is I increase, I check my, I increase, everywhere I see a K, I increase it to K plus 1. And that's all over my current term. Watch your factorials. This is K plus 1 factorial, okay? So I'm dividing by a fraction, which means it's K factorial over 3 to the K. So I'm gonna group these together. So this will be 3 to the K plus 1 all over 3 to the K times K factorial all over K plus 1 factorial, absolute value. Okay, so now we can start, you know, kind of combining similar terms. So what do I have? I've got 3 to the K, 3 to the K, they cancel. So I've got limit, K goes to infinity. So the 3 of the K's cancel and I'm left with 3 to the 1 times K factorial over K plus 1 factorial gives me 1 over K plus 1. I'm gonna leave this to you. You know how the factorials cancel each other out. Okay, but I'm left with 1 over K plus 1. So now look, K is going to infinity. So 1 over infinity, or 3 over infinity, this is going to equal to 0. 0 is less than 1, therefore this thing converges. Okay. All right, last one. This is going to, oh, sorry, D. D has a negative, which is nice because we have an absolute value, so it's going to get rid of that. I'll put it in the beginning. Oops. All right, whatever. To infinity. So this goes -1 to the K plus 1, K plus 1, all over -1 to the K, Okay. The absolute value gets rid of my -1. So this is K plus 1 all over K. So now K is going to infinity. Infinity plus 1 all over infinity. You know, I'm dealing with the coefficients here. So this is just equal to 1. Inconclusive. So I need to do, need a different test. This is chapter 5. We're going to learn all different tests that we can use to process this. Right now, the ratio test isn't the right test for us to be able to use because we're getting an inconclusive result. All right, so that's just, in essence, how we set up the ratio test. Now we're going to apply it to a power series. These are just generic series. And a power series means I've got x to the k. I've got some kind of a polynomial happening in there, okay? All right, so let's start working through examples. So example 2. So use to see, we're going to use this because this is a power series. So let's write this down. X to the n makes this a power series because I have, if I were to, you know, draw this, like sum this out, I would get, you know, 0 factorial x to the 0, right? That would be 1 plus 1 times x to the 1 plus 2 factorial times x squared plus 3 factorial times x cubed plus so on and so forth. It's a polynomial, okay? Which makes it power series is a polynomial. Okay, so let's, we're gonna do the same thing. So let's convert this limit as n now, n goes to infinity. So I've got n plus 1 factorial x to the n plus 1. Everywhere I see an n is my operating variable, right? So n, I'm increasing. And this is all over n factorial x to the n. But n is the thing that's going to infinity, not x, okay? X is my function variable, but n is the thing that I'm checking here. So now, limit as n goes to infinity, n plus 1 factorial all over n factorial is going to give us n plus 1. And this, right, is going to be x to the n times x all over x to the n. This is just going to give us times x, which I can write this as, I'm going to write it like x limit n here, because this is like the absolute value of x is just my multiplier. N is the variable that's going to infinity. So this is unbounded. So my limit does not exist. Okay, my limit doesn't exist. Then that means that our series, our power series, will diverge for all values of x except a, which is equal to 0. How do I know a is equal to 0? Because I look right here in my original power series. This is x minus a raised to the nth power. X minus 0 raised to the nth power is just x to the n. So this our a is equal to 0. So this is a point convergence. Our radius is equal to 0. Okay. Okay. You're starting to see what all these things are going to look like to help you be able to evaluate what's your function doing. Okay. Example 3. So we want to use the ratio test to talk about this one. I actually just want to enumerate this for the first couple of terms, just so you can see, you might recognize it. So when n equals 0, minus 1 to the 0 is just 1. 2, x to the 2 times 0 plus 1, this just becomes x to the 1 all over 1. Remember, because 1 factorial is equal to 1. So x to the 1 now, when n equals 1, I'm going to get a minus x to the 3 over 3 factorial. When n equals 2, I'm going to get plus x to the 5 all over 5 factorial minus so on and so forth. This, hopefully you're starting to recognize is equal to the sine of x, right? So this is Maclaurin. Our a equals 0 because there's no x minus a. X minus 0 is how you want to look at this, right? So my a equals 0, which is where it's centered. You'll be asked, you know, what's the center? What's the radius? What's the interval? What does that say? Well, we always need to write where it diverges and converges. Yeah, that's the whole point of the radius. That's the whole point of figuring out what the radius is that we're trying to figure out the range of values over which it's going to converge. And the ratio test is going to help you figure out what that radius is. So then you can write what your interval is. Let's keep doing it so you can see. So we're going to do the ratio test. So I'm using n. So this is the limit as n goes to infinity. Now, watch what's going to happen. I'm going to go minus 1 to the n plus 1. I don't even really need to include the minus 1 because I've got the absolute value, but I'm going to put it in there just for now. X to the 2, be careful. This is n plus 1 all over 2 n plus 1 factorial all over what I have originally. This is absolute value. Okay, so let's multiply things out. This is the limit as n goes to infinity. So I'm going to get rid of the negative ones. This becomes, let me write this out like this. So this, I have to multiply the 2 here. So this becomes 2n plus 2 plus 1 becomes x to the 2n plus 3 all over 2n plus 3 factorial all over x to the 2n plus 1, 2n plus 1 factorial, absolute value, right? You give yourself plenty of room to work because you need to be able to figure out what things are. We're going to multiply by its reciprocal, 2n plus 1 factorial, x to the 2n plus 1, right? So now we're going to get the limit as n goes to infinity of, right? So I've got, let's group these together, 2n plus 1 factorial, 2n plus 3 factorial, x to the 2n plus 3, x to the 2n plus 1. Okay. So now what you'll want to do is clean up. You should do out the factorials, right? So this is 2n plus 1 times 2n times 2n minus 1 times 2n minus 2, so on and so forth. So this, I'm going to leave it to you to actually work out what all those factorials are going to look like, how they clean up. It looks like this. So this is 2n plus 3 all over 2n plus 1. Okay. So then I'm going to get x squared all over 2n plus 3, 2n plus 2. Okay. N is the thing that's going to infinity, right? I have an n squared in the denominator. So as n goes to infinity, this thing goes to 0. Okay, which is less than 1. So this series will converge for all values of x, okay, which is what we know about the Maclaurin for sine. So we're going to say our radius is infinite, okay? And I'm just going to write down our center is equal to 0, okay? This is what things are looking like. So you can start to see how you're going to need to process it. All right, let's do our last example. I think we'll have time for one more example, which will actually show you an interval of convergence. And then when we meet again tomorrow, we'll finish up the examples for 4.5 and then we'll start 4.6. Okay. What are the radius and interval for the following power series? It's a power series, right? And this here is just for when we do the ratio test. We don't want it to cause us to bomb out when we have a divide by 0. So my ratio limit as n goes to infinity, right? I'm going to go 3 x minus 2 to the n plus 1 all over 3 x minus 2 to the n. So you can see why we would put that. This is just for the ratio test. So we don't get a divide by 0 problem. Okay, so let's clean it up. The 3's are going to cancel and goes to infinity. That's an infinity. This is going to be x minus 2, right? Now watch what happens, right? Because the n's cancel. So now I don't have any n's anymore. If I want this to converge, this whole thing has to be less than 1 in order to converge. So let me write that down in a different color. Okay, so there are no more n's to take the limit of, right? So I'm basically looking at the absolute value of x minus 2. The criteria for convergence is that it's less than 1 by the ratio test. Remember, we said that at the very beginning. By the ratio test, this thing has to be less than 1 in order for it to converge, okay? So I'm specifying that by my ratio test, okay? Right here, this is our radius, okay? All right, so let's summarize that in words. So when the absolute value of x minus 2 is less than 1, this power series converges, which means that our polynomial is equivalent to our function, okay? When absolute value of x minus 2 is greater than 1, power series diverges, right? That means that the error between our function and our approximation is too great that it's not really worthwhile using anymore. My question for you is, look, how come I'm not adding 2 to both sides, right? So I get x, you know, whatever. And the reason is this, because, right, on my polynomial itself, my power series is centered at 2. So I'm looking at absolute value of x minus 2. Okay, but we're going to use this to help us come up with our interval. Okay, so let's write that down. So our radius of convergence is equal to 1. Okay, our center is a, which is equal to positive 2. So x minus 2 equals 0. Solve for x. That gives me my a equals 2. So now my interval, of convergence. Remember, it was a minus r to a plus r. So I'm going to go 2 minus 1 to 2 plus 1. So we're looking at 1 to 3 is my interval of convergence. Now, if we'd already had chapter 5, we'll be able to go through, we're going to learn it later, how I can do a test to say, am I going to include both endpoints 1 and 3, or is it going to be an open interval? Should we go up to where we found a radius? Yes. Right here. Is that good? of the previous problem. So you're looking for this one. What I'll do is I'll scan in these pages this afternoon, and then I'll put up the intermediate, like the first 4 examples, so you can see it. And then but then I'll have to scan it in again for the next ones. Okay, so what I'm going to do is I'm going to actually stop here so that we can pick up tomorrow and then do another example. We're just going to keep doing examples to see how we apply the ratio tests to different types of power series and what they look like. How do we figure out what the radius is for different things? Okay. I suggest, taking a look at the homework for this stuff so that you can ask questions on it in office hours or next week. Okay, guys. All right, great. Well, I will see you tomorrow. Have a great afternoon, guys.
Thank you.
Thank you.
Thank you.
Thank you.